About flip-flops, registers and counters. Who's heard of flip-flops before? Who's not heard of flip-flops before? Right, okay. So a flip-flop quite simply is an element that can store one bit of data, either a 0 or a 1, as we'll see. So what I'm hoping to get through today are the darker coloured entries here on the list of objectives. We're going to learn about flip-flops. We're going to also hear about and learn about registers that store more than 1 bit worth of data, and look at shift registers as a specific example of a certain type of register that's useful in certain circumstances. And we're also going to be talking about how to describe memory elements using VHDL. So I'm going to start with a question. Why do we need circuits with memory? You look like you're itching to say something.
I mean nothing much. Just what do you memory? Just store something. Store a value.
Store a value, right? Without that, we would not have stored our photographs. We would not have stored these lecture notes somewhere for you to be able to retrieve them, etc. Whereby a lot of that memory is sort of offline memory. It's not really necessarily directly active. But yeah, they're sort of really obvious. Anything else? Yeah. That's a really nice point. Yes, you might want to detect whether something has changed or not. In particular, I'm going to emphasize that a little bit more because changes might occur really quickly, and it might be very difficult for us as humans to appreciate that they've changed, whereas digitally you might be able to notice a change that's happened very, very quickly, happened only over a period of a couple of nanoseconds maybe. So far the circuits that we've looked at have only been combinational. That means there's a direct relationship between the inputs to the circuit and the outputs. If the inputs change, the outputs change. There's a functional relationship between them, Boolean functional relationship between them. But sometimes we really want to remember something or know something, and then the relationship is not necessarily directly linear. Okay? So, for example, here's an alarm system. You have some sensor that detects the occurrence of some event, a memory element that then gets set by virtue of the fact that that event has occurred, and that raises an alarm which remains until the circuit is reset some way, usually by a user or some other circuit resetting the memory element. Okay? So the question is, how do we design these memory elements that can store some information? Note in particular that this sensor might be acting at a very high frequency. It might be very, very quick or transient that some event has occurred, and we want to remember that that event has occurred because it's important for some reason or other, right? It might be part of an airplane control system, for example, in which case, this could mean the difference between successfully continuing on with the flight or not. So, how do we create a memory element? Well, one way to do it, and I think we've come close to seeing it before, is to have two inverters connected together in a cycle or in a circuit like this. Now this circuit has two stable states, one where the wire labelled A is 1, and therefore the wire labelled B is 0. And of course the complement of that situation where the wire labelled A is 0 and therefore the wire labelled B is 1. Well, this is all very nice and good, but how do we change from one state to the other? This guy is obviously stable if it's in either of those states, but there doesn't seem to be a ready way of changing the state, of setting and resetting the memory, as it were. So let's have a look at a slightly more sophisticated cycle, in this case involving two NOR gates like this. Now I've put the truth table of the NOR gate over on the right here, and it's interesting for a couple of reasons. Firstly, if one of the wires, one of the inputs to a NOR gate is 0, then the output of that NOR gate is the complement of the other input. So if one wire is 0, depending upon what the other wire is, the NOR gate puts out the complement of it. On the other hand, if one of the inputs to a NOR gate is 1, its output is always 0. Okay, we can exploit that situation. In this case, consider the situation where both the set and reset inputs are 0. So we're operating in this part of the truth table up the top here. And that means that the output of each of these NOR gates is the complement of the other input. So if the wire coming out of this NOR gate here has the value Q, then this NOR gate here that's attached to the set line is going to output the complement of Q, or not Q, right? And that's going to be stable irrespective of whether Q is a 0 or a 1, okay? On the other hand, if we assert the set input, set it up to 1, well then we're forcing the output of the corresponding NOR gate to 0. And given that reset's left at 0, it's going to complement this 0, and the output Q is going to go to 1. We're forcing that output to 1. Okay? The opposite situation is where the reset is set to 1 and set is left at 0. In this case, we force Q to be 0, and of course the wire between the two NOR gates then is going to have the value 1. Interestingly, this state is also going to be preserved if we set to 1 as well, because then the output of both NOR gates is 0, right? Importantly though, Q hasn't changed, it's still left at 0. So irrespective of whether set is 0 or 1, when reset is 1, the output Q is going to be 0 here, okay? And this simple circuit is known as a latch. We have two NOR gates just connected together in a cycle. Now we normally draw them a bit differently. We draw this circuit in this way, which makes it more obvious that there's feedback between the QA here and the QB outputs, okay? So we have each output feeding into the other NOR gate as the second input, and of course we have our R and our S inputs. But the topology of the circuit is exactly the same as it is there. All we've done is just laid it out slightly differently and crossed the wires over. Okay, so this is the characteristic table for the SR latch. When S and R are both 0, depending upon what QA is, either 0 or 1, QB is going to be 1 or 0, the complement of that. If R is asserted, then QA is going to go to 0, and therefore QB is going to go to 1. If S is asserted, then QB is going to be forced to 0, and therefore QA is going to go to 1, right? And if both R and S are asserted, then both outputs QA and QB are going to go to 0. All right? Is that clear? All right, and we can trace that through with this timing diagram down the bottom here. We see here that initially reset's been asserted with S being 0, so that puts us into a state where QA is going to be 0, right? So that's where we see QA being low and QBs at 1 being high. Now when we drop R, it's just going to preserve that state because in this period between T1 and T2, both inputs are 0, so we're just going to be preserving the state that we had before R was deasserted. In this interval while R is low, when we assert S, well, that's going to force QB low, and as a consequence, QA is going to go high. So we see this leading edge of S going high is going to force QB low, and as a consequence of QB going low, we're going to have QA going high because R is low in this period here, right? So we have that inversion of the other input to the NOR gate going on. This state is going to be preserved even when S is deasserted again until R is asserted, in which case when R is asserted that forces QA low. As we see here, the leading edge forces QA low, and as a consequence QB is going to go high. If we assert S in the middle here, then both QA and QB are going to be low, right? But when we deassert S again, we revert to the situation where R is 1 and S is 0, so QA is going to be 0 and QB is going to be 1. Now right at the very end here, we see that both R and S are asserted, and therefore QA and QB are low in this interval here. And let's say that both R and S are deasserted simultaneously. Well, what happens then? What should the next state be of QA and QB if from the state where R and S are both high go to low? Sorry? No, it won't be the same because R and S were both at 1, right? Forcing their outputs to 0. Now, if both go to 0, then we immediately go into that state where the NOR gate is inverting whatever the other input is. Now, since it was low initially, they're both going to output 1. And what happens then? What happens when, as both R and S are being deasserted, both QA and QB are going to go to 1. And what's going to happen after they both go to 1? Yeah. Okay. If both QA and QB are 1 and both R and S are 0, then both NOR gates are going to have to complement those ones that are being input from the output stage of the latch, and therefore they're both going to go back to 0 again. And so we're going to get a period of oscillation in these outputs until eventually one output's going to flip just before the other. Why would it do that? Well, because it's nigh on impossible to have two physical objects that are exactly identical in terms of their resistance, their capacitance, and the latency that they will impose. And therefore, one of these NOR gates is going to change a little bit before the other, and as a consequence of that, you get a bias. You get that output flipping a bit earlier, and that will then dominate and determine what the ultimate state of the latch is going to be. But for a period of up to, well, it can be as long as, I think, 100 nanoseconds, you could have this oscillation going on here within the latch. All right? And we can't predict what the next state is going to be. So that's not particularly nice. Before we look at how to remedy that, let's have a look at the gated SR latch. This is a design that's identical in terms of the latch part over here, but we've added an AND gate to input with our RNS inputs to control the period at which those RNS inputs are seen by the latch via this so-called clock input. So for the period that the clock is high, whatever the R and the S values are seen here on R dash and S dash. Otherwise, both R dash and S dash are 0, and therefore the latch is preserving the present state. So when the clock is low, we're just going to be preserving the current state, but when the clock goes high, if R and S are both 0, if these inputs are both 0, we're still going to only have a 0 there, and therefore we're still going to be preserving the current state. And then depending upon whether it's the R or S input that's active, we'll have Q being set or reset. And unfortunately, we still have the situation that when S and R are both 1, and if the clock is high, then we're going to have 1 on both of these inputs, and therefore we're going to be in this situation that's depicted right at the right-hand side here, where both R and S are high when the clock goes back low again, and therefore we again enter this period of metastability where we can't predict what the next state is going to be without actually measuring it and observing where the biases are within this particular circuit. Okay? Right. Now, while this is logically easy to understand, this design, the way this latch, this gated latch, is usually implemented is using NAND gates rather than NOR gates. Okay? Before that, may as well make the point that the input when R and S are both 1 is, strictly speaking, it's an undesirable input because when both R and S are 1, R prime and S prime are going to be 1, and therefore Q and Q bar both go to 0, which is what we see here in this timing diagram. But Q bar is meant to be the complement of Q, and since they're both at 0, this is an undesirable situation. So we should recognize that this input, R and S both being the same, both being 1, is undesirable, or we might even term it illegal. So rather than implement the latch this way, more normally the latch is implemented using NAND gates because it uses slightly less transistors. The NAND and NOR gates are the same, but the NAND gates here are cheaper than the AND gates that we saw on the previous slide. Now, this design still has exactly the same characteristic table as we saw before. Only when R is asserted do we get Q going to 0. When S is 1, we get Q going to 1. But we still have this illegal situation when both R and S are set to 1, where we can't predict what the next state is going to be when the clock is deasserted. In terms of the behavior, well, NAND gates are slightly different to NOR gates. In this case, when any input to a NAND gate is 0, then its output's going to be 1, right? So if one of the inputs is 0, the output of the NAND gate is going to be 1. So in this case where the clock is off, we see that both of these inputs are 1. And that brings us to the second part of the NAND behavior. When one of its inputs is 1, it complements the other input, B in this case. And so we see the latch working in the way we expect it to when the clock is 0. Okay? All right. So to eliminate this, this illegal situation where both S and R are 1, we design or we introduce what's known as a D-type gated latch. So that's this guy, gated D latch. The change is that S and R are now hardwired to each other. They have an inverter between them. Pardon me. So now it's not possible for both S and R to be 1. Therefore, we eliminate that case from our characteristic table. So the characteristic table for the D latch, D for data, D being the single input, which determines whether or not the output is high or low. D is tied to S so that when D is high, the latch goes high. When D is low, the latch goes low, assuming the clock is asserted. So it has this characteristic table. It's a little bit easier or simpler than what we saw previously, because now it just matters whether the clock is high or not. If the clock's high, then if D is 0, the output's 0. If D is 1, the output's 1. So the waveform is a little bit more straightforward. Notice here in this region, T3, while the clock is high, D changes, and as a consequence, the output also changes. So we say that latches are transparent to the clock. So while the clock is high, it also happens in this period here, while the clock is high, we see whatever happens on the D input. That gets reflected in the output. So they're said to be transparent. That isn't necessarily desirable either. Maybe you want a memory element that just changes once, on an instant, every clock period, right? Doesn't have multiple changes like we see here in this period or in this period here. Then we can use the gated D latch as a component in something that's a little bit more sophisticated, which is known as a master-slave D-type flip-flop. So let's have just a look at the circuit before we talk about it too much. As we see here, we have two gated D latches wired back to back in series. And the only difference between the two is that the clock is inverted for the so-called slave latch that we see over here on the right. Okay? So if we think about the master latch here, when the clock is high, this master is going to see whatever is on the D input. And in fact, it's going to be transparent to it because it's the D-type latch here. So we see here in this first period, while the clock is high, D changes in the middle, and as a consequence, the output of this latch changes also during that period while the clock is high. But when the clock goes low, it freezes the output QM, because it can't change any further after the clock goes low. So whatever it was before the clock went low, that's where QM remains until the clock goes high again. Okay, so for the period that the clock is low, the QM value is stable, it can't change. Now, interestingly, when the clock goes low, that is precisely when the slave latch becomes active, because it has an inverted clock relative to the clock driving the master. And therefore, the slave becomes active, it sees what's on the QM wire here and responds, goes high. But because QM doesn't change, the output QS, the slave output over here, or Q overall for the master slave, can't change any further, right? It can't change until we have, again, an active high clock, in which case the slave is frozen. It can't change because the clock's low now for this part, while the clock is high again. Since D has fallen, in the meantime, QM goes low. And again, when the clock goes low, the slave becomes active. It responds to the fact that QM has gone low and therefore echoes that with QS going low. So what we see here is every time the clock is high, the master is active and it responds to any change in the data input, right? And reflects that in the QM output of the master. And when the clock goes low, the slave becomes active and it only sees what's on the QM wire, which doesn't change for the period that the clock is low. And therefore, it simply changes state and stays there. And so in effect, what happens, every time there's a negative going clock edge here, we have the value that's on the QM wire being transferred to the QS wire. And so overall, the master-slave flip-flop is storing what's on the D input when the clock goes low, on that negative clock edge. Okay? So, while latches are triggered by the level of the control signal, the clock, so for a latch, when the clock is high, it's active and it'll be transparent to the data inputs. So while latches are triggered by the level of the control signal, flip-flops are triggered on control signal transitions or edges. In this case, on a negative edge. So this is a negative edge triggered master-slave D-type flip-flop. The graphical symbol over here is that for a negative edge triggered flip-flop. We know it's edge triggered because instead of the word clock, we see this triangle, this notch in the symbol. That indicates that it's an edge triggered flip-flop. And the bubble on the outside of that notch indicates it's a negative edge triggered flip-flop. Are there any questions about this design at this stage that you formulated? All good. In which case, let's have a think about how we design a positive edge triggered D-type flip-flop. Could we change this design in some way to make it positive edge triggered? How about we just change the position where the inverter is there on the clock signal? In this case, well, when the actual clock is low, then the master is active, and when the actual clock is high, the master is frozen, right? So it's in that instant between going from clock being low to clock being high that we would freeze whatever is the value on D as the Q output of this design, right? However, this more complex circuit saves a number of NAND gates and a couple of inverters, and therefore it's preferred as the standard sort of positive edge triggered D-type flip-flop circuit. Now, I'm not expecting you to remember the circuit. Remember, you're going to have, it's an open book exam. You've got it there in front of you if you need it. Believe me, I won't be asking you to recall what the structure of the D-type positive edge triggered flip-flop is. But it is worth understanding how it works. All right? And it might be a little bewildering to look at the whole thing at once. So let's just break it down a little and think about, well, what happens when the clock's low here? All right? Remember our NAND truth table says that when one of the inputs to the NAND gate is low, it's got to have a high output, right? So only when one of the inputs is high that it inverts the output. So we see when the clock is low, this final stage, because the clock is low, the outputs of these two flip-flops, these two NAND gates, 2 and 3, at P1 and P2 are both going to be 1 because the clock's low. And as a consequence of that, both NAND gates 5 and 6 have one input that's 1, and therefore it's inverting the other input to the NAND gate, right? So Q and Q bar are reinforced. So far, so good? So let's have a look at the input to the circuit. We have our data input down here. Since P2 is 1, that must be inverted by this NAND gate. So P4 is actually D bar. And since P4 is D bar coming in here, doesn't really matter as far as this NAND gate is concerned because it still has a 0 coming in from the clock. But with D bar going up here, we have the 1 coming from P1 up here, which inverts D bar, so we have D up here on P3. okay? But neither the value at P3 nor the value at P4 can get through to the output of the flip-flop because both P2 and P1 are 1. And that's a consequence of the clock being low, right? So while the clock is low, you can't have any change in the output. However, let's consider what happens when the clock goes high. So when the clock goes high, we have these two NAND gates becoming active again. You know, they've got to invert their other inputs. So what do we see happening? We then see that this D bar input comes into this NAND gate, but we've got a third input to this NAND gate as well. And it just so happens that this NAND gate, P2, is going to invert the D to make this point P1 D bar. So we're going to have a D bar coming in from P1 and a D bar coming in from P4 into this NAND gate. And the other inputs are 1, so it's got to invert the D bar. It'll make that output D. Okay? And as a consequence of that, well, one of these, either P1 or P2, must be a 0. Let's say, without loss of generality, there's D bar that's 0, so D is actually 1. If P1 is 0, then that forces the output of this NAND gate to 1. And since that guy's at 1 and this guy's at 1, the output of this one must be 0. Okay, so it's set to that value. Think of the flip case. If D is 0, then P2 is at 0. That forces this NAND gate's output to 1. And together with the 1 that we have up here, given that D is 0, then P1 must be 1. We have two 1s coming in, must be a 0 going out at the top. So clearly we have the situation when the clock goes high that the output, the Q output of the flip-flop goes to D. Now what about while the clock is high? What if there are changes in D while the clock is high, which is also a possibility, right? Then we see that if D happens to be 0, then P2 is 0. And since we have a 0 input to this NAND gate here, it doesn't matter what changes you get in D, P4 is going to stay at 1. And therefore, you cut off the access for D into the flip-flop if D was 0 when the clock went high. And it'll do so for the period that the clock remains high, right? On the other hand, if D is 1 when the clock goes high, then P1 is forced to 0, and that forces the output P2 to 1 and forces it to stay such. And the same with P3. With P1 being 0, the output of P3 must be 1, right? And as a consequence, we still can't get new values of D coming through into the flip-flop. Okay? So in both cases, if D is 0 or D is 1, after the clock's gone high, we can't have any further changes to the output of the flip-flop. And therefore, it only transitions when the clock goes high. That's the only time it transitions. All right, that's probably a lot to take in. There's a lot on this slide. I suggest, think about it carefully when you've got a bit of peace and quiet, and hopefully it's clear. Otherwise, come and ask questions on Fridays. That's when I'm here to answer questions about anything that you've got. So one last point. The graphical symbol for a positive edge-triggered D-top flip-flop is as such, as has D input, Q and Q bar as outputs, has a clock with a notch on it to indicate that it's positive edge, or to indicate it's edge-triggered, and there's no bubbles, so this is a positive edge-triggered D-type flip-flop. So changes in state happen on the rising edge of the clock. So just to compare the three circuits that we've looked at, the D-type latch, the positive edge-triggered D-type flip-flop, and the negative edge-triggered D-type flip-flop, with a given clock signal up here and varying D signal as we see, The latch, QA, is transparent while the clock is high to D. So any changes in D while the clock's high, you see those on the output side of the latch. The positive edge-triggered flip-flop only cares about what the state of D is when the clock signal rises. So D is high here, and therefore we see QB going high. When the clock goes high again over here, we see D is low, and therefore QB goes low. As for the negative edge-triggered D-type flip-flop, it only cares about falling edges of the clock. So when the clock first falls, D is low, so there's no change in state. And the second time that the clock falls, D is high, and therefore we see QC going high. Okay? All right. How are we going there? Good. Any questions so far? All right, because we're going to start looking at how to specify latches and flip-flops in VHDL. How do we do this? How should we specify a latch or a flip-flop in VHDL? Any ideas? Yeah? Great, I'm glad you said it. I'm glad you said that first. You could have gone another way. But yes, clearly these are circuits that are based just on gates and their connections, so we can just describe the gates and describe the connections and thereby implement a structural description of any one of these circuit elements, right? Now I saw another hand up here.
I was just wondering if there's any preset code,
Yes, there are. And this is a really good question. So the synthesis tools work on patterns in your VHDL code. They look for specific types of idiomatic expressions that you've used, and know that if you use this type of code, what you want is this type of circuit element, right? And so yes, for these circuit elements that we've just looked at, there are very specific idiomatic expressions that we're going to cover now. And it's just like any other language. If you're talking with your mate, you use particular idiomatic expressions to convey specific meanings. And you're looking for those patterns all the time when you're listening and talking with your friends. Exactly the same with any programming language. Ultimately, the compilers look for those patterns and translate them. They've been optimized to translate them a certain way. Okay, there was another question?
It was like, do you know how you have the control statements like if, when? Is that the same idea? That would actually convert to a circuit diagram?
Yes, yeah, they do. I mean, that's precisely what I was trying to get across, that if you want to describe a mux, the most sensible way to describe it is to use a selected assignment statement with some signal select, right? That's true. You could use a process, you could use behavioral code, you could use an if then else statement, but it's overkill. It's not necessary. You don't need a process to describe a mux, because a process is reserved or is intended to describe complicated sort of hardware that isn't readily described structurally, or would be too complicated to describe structurally. So, I hope you also remember that last week we were talking about implied memory on Friday in particular. We saw this example of a process that had an if statement in it implying a mux. It has this, XNOR gate, which is checking whether A equals B, and when it's 1, it assigns a 1 to the output. But unfortunately, there was no default assignment to A equal B, And therefore, when A is not equal B, the circuit is forced to remember the state that it had prior to being triggered, or prior to this process being triggered. And therefore, it has to have some sort of feedback from what currently is the output back to the zero input on the mux. Okay? Not a very good design, and clearly an error. You should always, for a combinational process, always allocate a default value to every signal that you're outputting from that process. So, to describe a gated D-latch, we can do exactly the same thing. We have a guard here that when the clock is 1, just assign D to Q. So when the clock is not 1, we're not doing anything to Q. We're not changing it. So it has to keep that value. This is the idiom that you would use if you want to describe a latch. This implies a latch. That's what the synthesis tool would say. Code for a latch. Doesn't matter what you've called the clock. Doesn't matter what Q is. Doesn't matter what D is. You know, what names you've used. If it sees that pattern, it says, that's a latch. Right? And clearly, while the clock is high, this guy is going to be transparent so that the process gets triggered if there's a change in D. But only if the clock is high does that have any impact on the output Q. Okay? Here you see that the output Q is already low. We see a change in the clock. So this process is going to be triggered, and the clock is 1, and therefore it's going to assign D to Q. But Q is already 0, and D is 0, so there's no change in the output there. Okay. All right. So a latch has to have both the signals that you want to assign to the outputs in the sensitivity list as well as the clock in the sensitivity list. Otherwise, it's not going to work reliably. In fact, most compilers will check if your code misses something. You know, if you left the D out, you're probably going to get an error. Even with Vivado, it'll say, you know, it looks like you want to do a latch, but you haven't put D to the sensitivity list. Are you sure this is correct? Similarly, if you didn't have clock in there, it would say, well, hang on, clock's in the guard here. Don't you want it to be in the sensitivity list then? Okay. What about a flip-flop? So this is an edge-triggered device. Flip-flops are edge-triggered, latches are level-sensitive. So for a flip-flop, it's also called a synchronous element because it's synchronized with the clock. We only ever have the clock in the sensitivity list. That is the only signal you put into the sensitivity list when you're describing a flip-flop. Don't care about the guards, don't care about what other signals you might be putting on the right-hand side of an assignment. Does not matter. The only thing that goes into the sensitivity list is the clock. And in this particular case, we're then going to check, has there been some sort of signal transition on the clock? That's what this clock tick event means. And if the clock is now 1, having had an event on the clock, then assign the value of D to Q. Okay? Sorry. So this clock tick event is, this refers to a particular attribute, the tick event attribute on a signal clock, which indicates that there's been some change in value on that signal. Obviously, when there's a rising edge going from 0 to 1, that's an event. But so is going from uninitialized to 1, or from X to 1, or from H to 1. All of those are events. And all we care about is that now the value is 1, because that to us means, well, we've just had a positive edge, and we're now at a high value, and as a consequence, we want to remember what the value of D is right now. Okay? So when the clock changes, when it transitions, whatever the value of D is, that's what gets stored in Q. You see over here, well, there's another clock event, but the clock is now 0, so it won't assign the D value to Q. Here's another clock event, and the clock is now 1, so the value of D is 0, therefore it changes the output to 0. Okay? There's several ways of expressing this. Yes?
In this case, we don't need the event one, right? Because it can only be a clock event, because we have no other identifiers in the process. Like the first condition in the if statement.
No, so given that we only have the clock there as in the sensitivity list, yes, it can only change state on the clock. That's true, but technically this clock signal can have 9 different values, and we're really only interested in the 0 to 1 transitions, but there are all the others that that you might be concerned about as well. But that's irrespective anyway. The clock tick event, this is just the idiom that you use. I'm trying to think of another example where it would go, and none comes to mind right now. Believe me, we do need to have the clock tick event there. I'll try to remember what it is and explain it to you. Okay. But for the time being, you have to be I can see where you're coming from. Given that D isn't in the sensitivity list, you're not going to even be checking, you're not going to be entering this process unless there's some sort of change in the clock signal level. But I can't think of why it is at the moment.
Clock event, it would be positive and negative edge trigger. Oh no, it's still
No, because if you just dropped the clock tick event and just had clock equal 1, but that then is the idiom, it's getting close to the idiom that you would use for a latch, and I dare say the compiler will just say, hang on, are you trying to infer a latch here? Because if you want a flip-flop, you're going to have to add that clock tick event in there as well, all right? Okay, so I mentioned that any process that's synchronized with the clock is a so-called synchronous process, so as opposed to a combinational process. Combinational being this direct input-output relationship, change in the inputs, change in the outputs. So a synchronous process only lists the clock in the sensitivity list. That's one thing you've got to remember. Secondly, all assignment statements within the synchronous process, so all of the assignment statements, should be guarded with a clock tick event and clock equal 1 if it's a positive edge triggered. If it were a negative edge triggered, you want clock tick event and clock equal 0, obviously. And then finally, each signal on the left-hand side of an assignment is then the output of a flip-flop. Okay, so those rules you need to remember for how to specify a flip-flop in VHDL. Are there any further questions on this before I move on? Okay, so there's several ways of specifying flip-flops. This is commonly seen as well, where we have a process with no sensitivity list, so it's always running. And if we put as the very first statement a wait until statement, then that can infer a flip-flop. So if we wait until the clock tick event and clock being 1, and then all of the assignments that we make underneath that statement are the result of an assignment to a flip-flop output. So all of the signals that appear on the left-hand side are flip-flops. Okay? If we want to use this semantic, though, for synthesis, the wait until statement has to be the very first statement in the process. If it's buried down after several other assignments, etc., we can't synthesize that code. So this only works if we put that wait until statement right at the very front. So I basically prefer using this, idiom because I don't have to worry about that rule about waiting until. But you do commonly see this, particularly if you're synthesizing a clock in a test bench, let's say. So you might see it within code that you've been given. Okay? All right. So I think this might be a good point to have a break because this gets a little bit more involved, and then it'll be slightly more smooth sailing after this section on presets and clears. Okay, let's have a 5-minute break and then we'll start again. So I'll start again at 1 o'clock. Any questions?
One question with the lecture just now with the positive edge flip-flops. You didn't specify D in the list, sensitivity list, but would it matter if we do? Because
Yes, it does, because it triggers that code if D changes and clock hasn't had any, if clock is low or if clock is high, if it's not going through a transition itself.
but don't we have the condition for when the clock?
You do, but you don't want to trigger it when you. Again, it's an idiomatic thing that if you want to specify flip-flop, only the clock. For a synchronous design, only the clock in the sensitivity list. Okay? Sorry? Yeah. Week 7. Yeah, on the Tuesday. So this time, so 12 to 1, week 7. Right, let me resume. All right, so often in a system, when you start the system up, you want particular values established on the flip-flops prior to the circuit actually being active. That means we want to either preset or clear the value of flip-flops. I mean, the normal thing to do would be clear all of them so that you know that what you've latched is the value that was actually present, not something that was pre-existing in the flip-flop. So how do we design the circuits to asynchronously clear or preset the flip-flop? So this means to be able to set a value of 1 or to clear the flip-flop to only have a value of 0 when we initiate the circuit. Graphically, the way this is represented within the negative edge triggered D-type flip-flop is to have separate inputs for preset and clear with bubbles on them to indicate that they're active low. So this means that we have to drive that wire to 0, assert a 0 on there for it to work. Internally, that might look like this. So here we have our master and slave latches within the master-slave flip-flop. We have our clock coming in to the master, which is inverted for the slave part over here, as we saw before. So if the clock is low, then what we want to do is we definitely want to set the Q, if we were presetting, let's say, to 1. But if we want that value to remain for any period after we deassert the preset signal, then we actually have to change the output state of the master as well while the clock is low. And that's why you see a second input here into the master as well on these preset and clear signals. So when the clock is low, we need to override the output of the master so that when that asynchronous signal is deasserted, that signal remains on the output of the master so that the slave doesn't change value while the clock is still high as a consequence of that. Right. So it's important that we have to change the value of the master as well as the value of the slave while the clock is low. On the other hand, if the clock is high, then we really only care about the output stage here, the slave. So we only need to be concerned about changing the value here. That will be preserved because we won't have any change in the input wires here, given that both these NANDs have an output of 1. We've isolated the master part from the slave while the clock is 1. Okay? So the only issue here really is to determine how long does the flip-flop stay in the clear or preset state once we've preset it or cleared it. Is that obvious to you? You might have to think about this a little bit, but we've discussed the case where when the clock is low, we need to change the value of the master as well as the slave so that the slave doesn't get any new inputs when the preset or the clear signal is deasserted again. And on the other hand, if the clock is high, we only need to worry about the slave output. So how long is the slave going to be maintaining that preset or clear state? After the preset and clear signals are deasserted. Changes in which way? Let's say the clock's initially 0. I preset it, deassert the preset, and then I get a rising clock edge. What's going to happen?
Is this positive or?
It's negative.
So then it needs to be raised and then lowered.
So how long does the preset state stay?
Until the clock has gone from 0 to 1 back to 0.
Until the negative clock transition, right? True. What about if the clock is high? If the clock's high, we change the output. When is it going to change again? Assuming I deassert the preset or clear before the clock goes low. Well, when the clock goes low, the slave becomes active, right? And it's going to respond to whatever the output of the master is. And therefore, we can't guarantee that that preset or clear state's going to be maintained beyond the negative edge clock transition again. So in both cases, if we asynchronously preset or clear, that state is maintained until the next negative edge transition after we've deasserted the preset or clear signal, okay? For the positive edge triggered D-top flip-flop, it's a slightly more complex arrangement, bit of asymmetry here between the clear and the preset signal, but essentially the same arguments follow. So when the clock is high, right, then remember that these 2 points are then sensitive to whatever the input is and what the value is that's the output of this NAND gate to determine what the value should be on that wire. Because they get complemented. So having this not preset be low forces this output to be 1, and therefore together with the 1 here, the 1 there, and the 1 that's on the clear, the not clear line, since we're only either presetting or clearing, assuming we're presetting, we only have 1 inputs to this NAND gate, therefore this goes to low. This guy being low forces then, I think some, overriding the master output. So whatever the output was, it forces this to low. As a consequence of this being low, this output's going to go high, right? So that's when the clock is high. And when the clock is low, just focusing on the lower input here, it's symmetric. We're only concerned about the slave output and overriding whatever the value is on the slave output, because when the clock is low, we know these 2 NAND gates are both outputting 1s, right? So that means we need to pull this guy up, which is done by, if clear goes to 0, then this NAND gate's output goes to 1, and as a consequence, with the 3 ones that are coming into this NAND gate, we're going to have a 0 put out on Q, thereby clearing that flip-flop. So in either the high state or the low state, we're able to clear or preset this flip-flop, and it's a similar argument again as to how long that preset or set state is maintained. It'll be maintained until the next rising clock edge. That will ensure that it's cleared. Okay. Right, are there any questions on this right now? I think I'm probably stretching the limits of what you're able to take in the one lecture, but Are there any questions you have right now, burning questions? All right. Well, we've talked about asynchronous ways of clearing and presetting, so I'm going to push on regardless. Even though I know you can't take anything more in, I'm going to do another 10 slides, another 12. Right. So, we've talked about asynchronous clearing and preset. Look at me, don't worry about the slide for the moment. We've talked about asynchronous clearing and preset, right? Now I'm going to talk about synchronous clearing and preset. This means I want to override whatever the D input is and know that on the next active clock edge, be it a rising or falling one, depending upon what sort of circuit it is, I want to enforce a particular output on that Q output. In this case, by gating the D input with a signal that is active low, clear in this case, whatever D is, I know the D input's going to be 0 when that not clear line is 0, right? When this input is 0, the output of the AND gate is 0, and therefore on the next rising clock edge, Q has to go to 0, right? It's synchronous because it happens in synchronicity with the clock. It doesn't change as soon as I assert that signal, it changes when the clock edge comes along. Hence, it's a synchronous preset or clear. Okay. What if I wanted to make this, rather than a clear, a preset? How would I wire that up? If I wanted to force the Q output to 1 synchronously, yes?
Change it to just preset instead of not clear and then make it an OR gate.
Okay, the important part is changing the AND gate to an OR gate. I think you said that, did you? And having an input to that OR gate being, yeah, well, you'd want it, I guess, to be an active high input being preset or something like that. Alternatively, you could make it a NOR gate and then have an active low input, right? I think. Now that would be conditionally inverting it. It'd have to be an AND gate with an active low. So if you made this an AND and had not preset, then when preset is low, you're forcing that NAND gate to be a 1, the output of the NAND gate to be a 1, right? Are you convinced? I'm debating with one person here. Remember that the output of a NAND gate is 1 when one of the inputs is 0. So if we wanted to make an active, a synchronous preset, the way we would do that is to have an AND gate with a preset, active low preset coming into our D input of our positive edge triggered flip-flop. Right? Because when this guy's 0, that is forced to 1.
But then when D get flipped?
Sorry?
Will D get flipped?
Well, only if only if Q was 0 before.
But if preset is not on,
Mm-hmm.
then D is 0.
If preset is 1, if this wire has a value of 1, then the NAND gate is just, well, it's inverting, so we have to have, I guess, an inverter on our data input. Yes. It's all, doesn't matter which way you go, it looks like you're going to involve several negations in order to synchronously preset. True. Okay, how do we code these asynchronous resets in VHDL? So, while I previously said you can only have the clock in the sensitivity list for a synchronous flip-flop, when you want an asynchronous input, you also list that in the sensitivity list. Reset here has an N on the back to indicate it's active. It's reset not, or not reset. So if the reset is active, if it's 0, then assign a 0 to Q. Otherwise, if it's an active clock edge, if it's a rising clock edge in this case, assign D to Q, right? So this guy's going to override while ever reset's high. So only when reset's low again, sorry, this guard is going to override while ever reset N is low. Once reset N is high, then the positive clock edge guard will apply if there is an active edge on the clock. Is that clear? Okay. Important to remember also that you should only ever assign a 0 or a 1. You'd put a 1 there if it was an active set, right? If it was a preset. So only a constant here, don't put another signal in there. Otherwise, again, the synthesis tools won't like you because this is the way that these are internal operations for the flip-flop. You can't necessarily assign some other value to it. Okay, similar situation. This is for a synchronous reset, as you can see, because we're waiting until an active clock edge comes along, and only then are we checking whether reset is active or not. So it's a synchronous reset, as opposed to this guy that's asynchronous. Okay. How would we code this using the alternative code for a flip-flop in a process, behavioral code for a flip-flop? So if we wanted to use the guard if clock tick event and clock equals 1. So then it should look like this. So we have this is a synchronous reset on our flip-flop because it's subservient to that clock edge coming along. All right, so we've talked about single bit structures called flip-flops. Registers are just vectors of flip-flops or collections of flip-flops. So this describes the code for an 8-bit register with an asynchronous reset. So in this case, the D input is 8-bit and the Q output is 8-bit. If there's a reset, then all of the bits of Q have to be cleared, and because it's a multi-bit vector, that has to be double quotes surrounding that constant value. Otherwise, if it's an active clock edge, assign the vector D to the vector Q. Okay? All good? If you wanted to make an n-bit register, then we can use what's known as a generic parameter, as is illustrated up here, for n, which is given the default value of 16, in order to define how large these vectors are that we want to store. And in that case, if we want to clear the contents of the flip-flop, we don't know exactly how many bits there are. Well, we know there are n bits, but we can't code that as a constant, n bits within double quotes. So this is the idiom that you use if you want to clear all of the bits of Q in one shot. You assign others is assign 0 to Q. And if you have an n-bit register like this, you can instantiate it using whatever size you wish by overriding the generic parameter using a generic map. In this case, we're inferring an 8-bit register. So here, the vectors are 8-bit long, but we're using our generic n-bit register as a component and overriding the size of n by using a generic map statement. Okay. The rest is the same. Any questions? All good? Okay, so this illustrates a shift register, a 1-bit shift register, in which case the input bit in here is loaded into this leftmost flip-flop when we get an active clock edge. And that, of course, appears on the Q1 output after the positive edge comes along. This is a positive edge-triggered flip-flop. And the next flip-flop along is going to transfer this value Q1 to its output Q2 when the next rising clock edge comes along. And similarly, for the subsequent flip-flops to the right, each one transfers that bit one clock cycle later to the next flip-flop to its right. So here we see a rising clock edge with a 1 on the input gets transferred to the Q1 output of that first flip-flop. On the next rising edge, I've tried to illustrate the rising edges here on this clock. That value that was here, the Q1 being 1, gets transferred to Q2, but Q1 becomes 0 because at that point in time, the input to the flip-flop is 0. And so we see as time goes on, with changes in the input, they get transferred out to the output of the shift register, as we see. The bits get shifted to the right. Often we want to read these values in parallel out of the shift register, and we might even want to establish a value on the shift register in parallel and then shift the bits out sequentially. This allows us to translate parallel data into serial data or serial data into parallel data. So in order to do that, here's an example of a 4-bit shift register which has a serial input here which could be shifted sequentially into each of the flip-flops that appear here, from the most significant bit here over on the right to the least significant bit on the left. Or, based on this active low shift, active high load input signal, this guy here that controls this inverter, when we're loading, we could take 4 bits in parallel and load those directly up into the flip-flops that we see up here. So in effect, the circuit that we see below each flip-flop is a 2-to-1 mux. They're all sharing this, this shift load input. That's the inverted version, is the red line. The blue line is the not inverted input. And so each collection of 2 AND gates and an OR gate represents a 2-input mux, a 2-to-1 mux, as input to the corresponding flip-flop. So we see the output of one flip-flop being not just sent to the top, but also being presented as input, which when we're shifting, when the inverter output is active, gets transferred into the data input of the next flip-flop on the next active clock cycle. In that way, depending upon what we set this shift load control signal to, we're either shifting the contents of the register over by 1 bit at a time, every clock edge, or we're loading in parallel data from external to the register into the register. Okay, so we could read a word in parallel in 1 clock cycle, and then over, in this case, 4 clock sequences, read out of Q0 serially what are the bits that we loaded into, what were the bits of that word. Similarly, we could be loading over 4 clock cycles via the serial input into each one of these flip-flops, and then in 1 clock cycle read the contents of the whole word that was shifted in serially. How do we code that up? Well, here's the code for a D-type flip-flop with a 2-to-1 mux as input. So we have a D0 and a D1 input, a select input that tells us which one of those is meant to be stored in the flip-flop, and we have our Q output from the flip-flop as well as the clock. In this case, we use the wait until idiom to control the flip-flop. And when we do get an active clock edge, based on the value of the cell input, we either load D0 or D1 into the Q output of the flip-flop. So that's literally just describing one stage out of this structure here where we have a 2-to-1 mux coming into a D-type flip-flop. So to describe the shift register overall, we want to instantiate 4 copies of this mux DFF. Now it could have also used the if clock tick event and clock equal 1 semantic and had the mux subservient to that. That's equivalent in terms of what would be synthesized. So for the hierarchical code of a 4-bit shift register, we then want to use that mux DFF as a component, declare it as a component, and then instantiate 4 copies of that mux DFF. Something that occurs here, though, that you haven't seen before is that we have the Q bits output from our DFF, but they're also being used as input for less significant bits of our structure over here. So we see that the Q bits are both output from a component and being used as an input. So their mode has to be different. It can't just be in or out. Remember, for our component, Q is an output bit, whereas for as an input, Q3 plays the role of D0, is an input bit to the flip-flop. So we have to declare the signal Q to be of mode buffer. And that allows us to both read the contents of this signal Q and write to it. So internally here, we're using Q both on the right-hand side, on the left-hand side of an assignment and on the right-hand side of an assignment. And therefore it has to have this special mode where it's both serving as an output from a component and as the input to a different component. This does not mean that we can write to Q from outside of Shift4. It only means that internally we can use Q on both the left and right-hand side of assignment statements. So another way of specifying the same structure behaviorally is to have one process active on a clock edge. If load is 1, then we're putting the values of P into Q, the input P into Q, so it's the parallel load. On the other hand, we want to shift Q1 into Q0, Q2 into Q1, and serial into Q3, etc. Okay? So these are specifying the same thing. These are structural specification. This is a behavioral specification. Okay? We've still got our buffer up the top here because clearly now we're using Q on both the right-hand side and left-hand side of assignment statements. Does it matter what order we list these statements in? If it were a coding language, it's not. It's a description language. Yep. No. Okay, so they're going to be evaluated sequentially, true. So Q1 is going to be assigned to Q0, and Q2 is going to be assigned to Q1. But what value are we assigning to these guys, and when does that assignment actually happen? Remember, I told you on Friday, that assignment doesn't get actually committed until we exit the process, right? So what's the value on the right-hand side? It happens to be the value that you have when you enter the process. Okay, so the order in which you list these doesn't matter. So this is just as correct. Okay? So importantly, the value that a signal has internally to the process is only the value that it had when it was entered. The value that gets written to a signal when you leave a process is the only one that gets committed at any point in time. I think I have one more slide for you to be swamped by. We saw last week the for generate statement, which acts effectively as a macro to repeat several combinational statements or instantiations. The corresponding syntax for behavioral synchronous sequential statements is the for loop statement. So just as we saw on the previous slide, several assignments here to Q, means exactly the same. Expand this to read Q0 is assigned Q1, Q1 is assigned Q2, and so on, up until Qn minus 2 is assigned Qn minus 1, and to Qn minus 1 assign the serial input bit. Right? This is for an n-bit shift register, whereas the previous one was a 4-bit shift register. So this is useful doing a loop when you don't know how many times that has to be expanded, obviously. Okay. So that's been the workout for today. Sorry. But it's over. You can go now. Are there any questions?
For the gen bits on the left of the for syntax, does it matter?
Yeah, the label.
Yep.
So this is just a user declared name. I think you can get away without having the label, but it is typical to have a label associated with it. How much time do you guys feel you have to read and try to work at understanding the slides in your own time? Is it 1 hour or less? 2 hours? 3 hours per lecture? 4 hours? 2 hours. So roughly the same as the lecture time, is it? Any other comments? 3? 4? Oh dear. That's hard work. Do you get it though? Good. Who's looking at the book at all, the text? Does anybody use it? Do you find it helpful? Yeah. So it's better than my explanation, isn't it?
It's more detailed and more simple.
It's more detailed, yeah. That is true.
First, and then you read the slides, and it's going to be much easier to grasp.
Yeah, but the slides follow the text very very closely. Yeah, true. Any other comments? So if I could just have a quick show of hands, how many people are spending sort of more than 2 hours per lecture understanding it in their own time? And how many less than 2 hours? Yeah, so it's about 50-50 by the look of it. Okay, fair enough.
Maybe more than 2 on the labs, though. Most of the time.
Oh, the labs will probably take more than 2 hours, yeah. I estimate, I had to do it the other day because we had to update the outline for some reason or other, and they asked how much time do the labs take, and of course it's pretty hard for me to judge how long it's going to take you to do it, but I estimated 70 hours all up over the course. So roughly 10 hours per lab on average.
I think you learn a lot in the labs too.
Sorry?
You learn a lot.
Well, absolutely. I did try to say that right at the start, you know, do the labs, that's where you really need to do the work. Yeah, good.
The labs and the practice questions are like the most.
Say again?
The labs and the practice questions,
Yeah.
like the ones we do on Friday,
Oh, good.
they're the most
Useful.
chunky part.
Oh, good. All right. Okay.
The lecture slides take 4 hours because I'm going
You were the one that said 4 hours, didn't you?
Yeah, because I'm doing questions.
Yeah, yeah.
If I didn't
Try,
do
oh, you mean the exercises? Or do you mean the ones that I ask on the slides?
yeah, when you ask me, if
Okay.
I didn't do those, it'll probably take 2 hours.
Right, I see. Okay.
That's why I say 4 hours.
It seems like many others say 4 hours too, though.
Yeah.
And normally if I were reading it, I'd also be trying to answer those questions, because otherwise, what's the point?
Yeah, true.
Yeah. Okay, all right, thanks for that. Yeah.
Just for this exercise, so I'm not too sure if it's the right, because it did say simplest. It said this, so we have to design a circuit to determine whether two 4-bit numbers are equal.
Oh, okay.
Yeah, but it did say the simplest, but the one it came up with is using a subtraction for a 4-bit adder. And it just subtracted to see if it's 0.
Mm-hmm.
I feel like it's a bit too much, because it is.
Yeah. So what if you just had 1 bit, 2 1-bits, and you wanted to know whether they're equal or not?
Two 1-bit. Oh, an AND gate. No, because if they're equal,
No.
it'll be a.
Not an AND gate.
It wasn't. 0, 0, 1. For that. No, when it's a NOR, it's NOR. If it's a NOR, wait, let me tell you. If it's a NOR, then, or if they're the same, you get a 1. If they're different, that should be a 1.
What's that?
Oh, an XOR.
Sorry?
XOR.
Yes. And what does it tell you?
If they're the same or not.
No, it doesn't.
But when
What does it tell you? When is it 1?
it's 1 when they're different.
Yes.
A, B, and then 0
So
when they're the same.
what would tell you when they're the same?
The
What would the,
output?
what would the output look like if the gate is meant to tell you that they're the same?
Sorry, could
What
you?
would the truth table be for same?
Would be same as in
Are
that
they
would
the
be
same?
a 1, 0, 0, 1.
Good.
Is that what
Yep.
Um,
And what's the relationship between those two?
complement.
Yeah. So this is really just X norm, which is A exclusive nor B, right? So,
Oh, and I just need 4 of them.
yeah. But you've got to wire these together. How are you going to wire them together? What joins them together?
Is
So we want that this one is 1, this one's 1, that one's 1, and that one's 1.
Yep.
So what would tell us that all of them are 1?
And
Yeah.
yeah.
And
Okay. Yeah.
does that
No.
make sense?
Yep. Yes.
Bit simpler than the full adders. You don't need the full adders.
Yeah.
I'm sure that will do it as well. Like if you had to do it, it's perfectly acceptable to subtract the one from the other and check that all bits are 0.
Thank you.
Okay, no worries. No worries, see you.